the same function using 7 core fields, you won't use 8 core fields because more material requires more energy, right? Okay, so those are quite interesting, and we are not making any conclusions yet. But this kind of a density optimization might be interesting phenomenon to look at in these systems, and whether or not the coherence or delocalization will play a role in this is also something would be very interesting to investigate. Last part, not much time, but this again, case 1. Okay. Now I talk about the density optimization. Now the next one is why. If we just let's look at case 1 and why it's so efficient. What's the key of its efficiency? The structure factors controlling the efficiency of labs in PS1. So adopt the PS1 model that's published before. It's actually not very important. We can take arbitrary models to get the same, I think, the same conclusion. But in theory, what we can do is we can randomly pick up 1 or 2 or more core field and remove it from our model. We can get rid of one of the core fields and use this to identify important sites for energy transfer for LiHAPS state. So when we delete one site, it's not that interesting. We delete 2 sites, arbitrarily choose 2 sites to delete. You have thousands of possibilities, and here we plot the quantum yield of those 2 sites deleted networks. And this is nothing. This is just to spread it out so it looks better. Okay. So what's interesting here is you see gap between them. Okay. Most of them are still very highly efficient, but some of them, the efficiency decreases. Those are green, so it's not very clear. But here, we can get to less than 90%. And if you go into look at all those points, all of them have site 3 deleted, meaning site 3 is important. Then others, those lower efficiency ones, have a site 70, 33, 32, 71 deleted. Okay. And if we look at this in the PS1 structure, it's quite clear that the site 3, site 2, 32, 33, those are important sites. And they actually, my function as energy wires, that this one conduct energy from this frame to spatial perturbation center sitting here. This one responsible for this, and this. So there are some we call gateway sites that are important for energy transfer or light harvesting in those structures. And we can keep deleting. And if you kind of keep those gateway sites untapped, you delete those sites there. Then you can delete up to 20 sites, this plus the quantum yield and the accumulated distribution function. So basically, if you delete 20 sites, 10, 5, 2, not deleted at all, the distribution is quite similar. Basically, you can remove up to 20% of the core fields in the antenna and not affecting the function of the system. Okay. Again, I don't have much time, so I'll skip this. So we actually studied some network analysis, some graph theoretical measure for the efficiency, and some of them actually correlates very well. For example, this one, connectivity, correlates with quantum yield. High quantum yield structures has higher connectivity. And hopefully we want to use this kind of stuff. Also, there are some that actually are not correlated. There are some insensitive ones. They are not correlated with quantum yield. And hopefully we want to use those quantum network measures to tell us a highly efficient network, what's the required structural features of those highly efficient networks. Okay. So let's go back. Finally, let's go back to this picture of a jungle here. And hopefully I convince you a little bit that within this jungle, in order to perform photosynthesis, to convert solar energy into useful chemical potential, we need quantum mechanics. Okay. And there might be more systems that will require quantum mechanical explanation in biology. So this one I modified. So my colleague, Professor Yao Jin, sent me this picture, and I think it's wonderful that I modified this a little bit. I called then this quantum mechanics in the Amazon jungle. Can we find more quantum bits? Okay, and actually there might be some. Okay, in the past 2 or 3 years, there's an emerging field or development of so-called quantum biology. People started to look into more details or to kind of propose revolutionary ideas to explain biological phenomena that before this you wouldn't dare to think about using any quantum mechanical principle to explain it. I think photosynthesis is an obvious one. I myself quite confident this in quantum mechanics is required for photosynthesis. There are proposals for for quantum effect in bird aviation using radical spin pairs. Okay, how you smell might be important. In quantum mechanics might be important in how you smell because some receptor of fruit flies might actually identify different vibrational modes of the molecules, not the shape of the molecules. Vision actually is, I'm quite sure there's quantum effect in there. Okay, long-range electron transfer, anion catalysis, some proton transfer requires photon tunnel to achieve a very high efficiency in those enzymes. For a review, I point you to this paper just published this year on Nature Physics. We have kind of a summary of all this in there. So finally, I want to acknowledge my students, my funding agencies for the possibility to do research, which I enjoyed quite a lot. And I thank you for your attention.
Beautiful talk. We can have a few questions before moving on to the panel discussion. Yes.
Thank you for your talk. In part 1, you talk about that you can measure the quantum coherence by nonlinear optics.
Yep.
And among the nonlinear optical effects, why did the research team choose to? I think it's four-way mixing, right?
Yeah, it's a four-way mixing span.
Why did they choose four-way mixing in order to measure? Thank you.
So this question is actually I think the easy answer would be you need a nonlinear technique, and then in an isotropic ensemble sample, the lowest order that you can achieve is the third order. So you use four-way mixing. But then before this has been done, I think people have, especially Graham Fleming and his friends, basically, had accumulated quite a lot of experience in this so-called photon echo technique. So this is a natural generalization of the photon echo technique. So there's also a continuity in how they develop the experimental technique. But third order is the lowest order you can do in this kind of system.
Other questions? So the details of this, I mean, you have these complexes, and the detail of these molecules, is it important or just the energy levels?
Energy levels, basically. Because I think in recent years, people started to look into more and more about the details of the molecule. And actually not just the molecule, the environment, the protein environment that's surrounding the molecule. The protein environment actually tune, adjust, and change the energy and the behavior of those chlorophyls. Okay? But in our model, we use a very simple two-level system, ground state, excited state, to describe it because the environment are modeled by a bunch of vibrations. So it's basically spin boson type of approach. Yeah.
In the energy transfer process, what carries the energy? Is that photon or the electron?
Electronic excitation, electron hole pair, acetone.
Okay.
Yeah.
But the energy is carried away by photons or?
Carry away. I mean.
Transfer.
Yeah.
It goes transfer. Then when it reaches the reaction center, you use that energy to induce electron transfer.
Okay.
Okay, that actually induce a long-range electron hole pair, and this separation can generate a chemical potential to drive.
So you have no problem to supply the electrons
No.
to reach.
No, but I wouldn't say no problem. Actually, this very well designed electron transfer chain. For example, in plain photosynthetic system, the electron comes out from photosystem 2 has to be transferred through photosystem 1. Then so there is a well developed a lot of downstream electron transfer reactions coupled with this.
But you need to supply the electrons from the beginning in order to.
Oh, the electron is in the molecules, in a spatial pair. Okay, so the spatial pair, one electron from the spatial pair goes to other place. Then there will be a cytochrome B5 come and bind and transfer electron from one heme to the spatial pair. So the electron can be replenished, and then yeah.
Okay. More questions before the panel discussion? Yes.
So in the talk about this coherence between these two energy layers.
Yeah.
It's like dimerization. But
Yeah.
How about consider like 3 sides more than 2?
I think in 3 sites the same general picture of using clustering to enhance coupling, then tune the energy. This kind of using delocalization to tune energy and the use designed energy scape to efficiently transfer excitations. This should be general. Yeah, of course we study a diamond system. Even in a diamond system, we cannot explore all the degrees of freedoms. We only choose 2, right? We have to fix others. A trimer will be too complicated for us. But I think the general picture should be the same.
Okay, more questions? All right, let's move to the panel discussion. Please, the panel members, please to move forward. We have a group of distinguished scientists in the panel. They are Chen Hengyu from NTU Physics, and also the speaker, and also Guan Xisen from NTU Physics. Mitsutoshi Hayashi from CCMS, the Condensed Matter Center, and also Gao Yingzhe from NTU Physics. Please go to the front. Are free to ask the panel member questions, and the panel members can ask questions to each other.
So this is supposed to be like some Rome arena or something. No.
Or just exchange ideas.
Exchange ideas.
Yeah.
Okay, let me start. Okay, I think as the speaker said, it's very amazing how the quantum coherence or property of quantum cohesion can survive in biological system. Okay, even as a room temperature. Okay,
Right.
so this is quite amazing. But I don't know. Have people reached consensus say that okay, how this quantum cohesion can survive?
Well, I guess first of all, if you step back and look at the effective Hamiltonians, how we describe the system early in the late 90s, it's not that surprising, in fact, because it's actually quite well known that those protein environments are sort of, so this sort of a general rule that the protein environment surrounding chlorophylls or those photosynthetic pigments are sort of hydrophobic, and they coupled to the chromophore, the excitation, actually in relatively weak. The reorganization energy is usually less than 100 Webb numbers, although it's comparable to the electronic coupling in the system, but it's not overwhelming larger than the electronic coupling. In a sense that this actually plays in, it's in the intermediate region, and the system-based system environment coupling are not that strong, so the phase in the coherence effect are not that strong, protected by the protein. Yeah. And how it's been protected? So there are several proposals. Even myself has proposed that correlation motions in the protein might play a role in there, but that part is more controversial. Yeah, there's no consensus on that. But we know that if you took a Hamiltonian proposed in the late 90s, you don't need anything new, and just run a Redfield dynamics, you see isolation.
Well, yes, of course, if coupling to environment.
It's weak, yes, yes.
But would it be possible that because the coupling, there are some studies in quantum dynamics. Okay.
Oh, okay.
So
The coherence free.
it's not actually well, it's similar, but they say because the coupling between the system and environment eventually results in
Point of basis.
coherence or something.
Yeah.
But that picture is because coupling is weak. But if coupling is strong, then system and environment form one state.
Yeah.
Okay. Then the system coherence can survive much longer because the coupling is strong.
Yeah, I understand what you say. Yeah, that's also a possibility. But because this is excitation energy transfer, the excitation entity itself is actually a charge neutral species. It's coupled to the environment. It's normally in the weak coupling, weaker side. But I think if you look at electron transfer problems, that's also actually quite significant in biological systems. Not even in photosynthesis. I didn't mention in the reaction center you have electron transfer. I already talked about electron transfer several times in my talk. Now, in the electron transfer or charge transfer, charge separation scenario, you have a real charge moving from one side to the other side. And that long-range electrostatic, much stronger electrostatic interaction results in much stronger electron environment couplings. And at that scenario, it might be more important. Yeah, so maybe if you look into electron transfer in biological systems, then this kind of induced coupling through environment, okay, could play some role over there. Yeah.
Well, there's a big community in quantum computing where the entanglement or quantum coherence between particles is very important, and Professor Guan is an expert on this. So I guess what he asked is that how come the biological system can reach such efficiency that seems that in the quantum computing community desire so much, but it's hard to get.
Well, I would say that the publication of that 2007 paper, Nature paper I mentioned, actually generated quite some interest from the quantum computing community. Many researchers in that field actually come to this field to explore possibilities in photosynthetic systems. I guess now the idea of using that as a quantum computer actually was proposed by several people at that time. But eventually people actually recognizes this dephasing decoherence is actually very comparatively much stronger than in sort of artificial quantum qubits. Okay, so it's probably not a suitable system for doing quantum computing.
So the quantum computer requirement is much higher?
Much higher actually, much higher. But then I think now the noise threshold is something like 10 to the -5, -6 for scalable quantum computing, scalable quantum error correction.
Okay, well, right now people say it's 10 to the -4 to 10 to the -3.
Uh-huh.
So it's reduced.
Okay.
Before it's even stringier.
Stringier, I see.
Yeah. But now people, well, but all these studies based on some simple model.
Yeah.
Okay. And
Yeah.
they run some numerical study
Yeah.
and they're saying that 10 to the -3. 10 to the -3 means a quantum gate with error less than 10 to the -3.
Yeah.
So the fidelity should be 39. Okay.
Yeah.
It's 0.999.
Yeah. And this is 97%. So yeah, so that's much higher.
But still, the quantum computing community, if you read the paper published in Science or Nature, the fidelity normally, okay, is 80 something. Then that would be natural science already, okay?
That's also true.
So still long way to go, right? If you want to have scalable.
Yeah, you may have mentioned some other biological systems like bird aviation and
yeah.
vision. Do those systems have higher fidelity in your quantum?
Probably not.
Okay.
Probably not. The quantum yield for vision, it's a cis-trans conversion is 67% quantum yield, but that is enough to achieve almost a single photon detector in vision.
Okay.
But the number you quote, the threshold, I think it's different things. Okay.
Yeah.
One is quantum gate operation, the gate fidelity.
Mm-hmm.
Quantum yield is energy transfer efficiency. So it's slightly different things.
Yeah.
Okay.
But then I think in the past few years, also since 2007, I didn't actually mention because that will be a huge literature on that. Many people have applied tools in quantum computing to study this kind of a system. For example, investigate entanglement in FMO, to investigate effect of entanglement in various geometry of energy transfer networks, like that. But normally they look at the small networks. And I think the behavior of small network might be different from the behavior of large network. And in natural Lagrangian system, a large network is quite important. Okay, because the molecular light absorption cross section is very small. You need a lot of molecules to absorb sunlight and funnel that energy to reaction center. To drive the engine, you need to funnel a certain amount of energy to it. If you cannot achieve that, the engine will fail, actually. Yeah. So maybe a direction that can be looked into is if we can have more tools, more different thinking from physics, okay, to look at this kind of a phenomenon. I talk about the last two examples intentionally because I think those sort of network analysis topological analysis, okay, would be useful to actually understanding the behavior of large network. And that's certainly not the expertise of chemists like me. Okay, maybe some people in mathematics or physics will bring a more useful tool to us. And that's, I think, will be useful if I come to this seminar.
So actually, I want to ask about this network analysis. So it's apparent that the structure of the network seems to be important in your analysis.
Yeah.
But can you say more about it? Since you were running out of time, so maybe let's give us some hint of.
Connectivity is important. Geodetic distance, so the average distance between two convoys, it actually has anti-correlation. So no, sorry. If the geodetic distance, average distance between sites are longer, then it has more efficient energy transfer, more higher quantum yield. That's what we discovered. And that,
the reason why? Because it's
that
kind of
might,
counterintuitive.
Yeah, but that might imply some sort of cluster of a certain size will be important.
Okay.
Yeah, and we need to actually, so like I said, we are not an expert in this. I need help actually.
Well, I'm completely layman in this field, but then this quantum mechanics is more. You know, for the condensed matter system, so at a certain stage, then you can do abelian calculations.
Yeah.
So for this field, are you at that stage?
No, not yet. Not yet.
Guessing some sort of Hamiltonian,
yes,
which looks like a quantum and thing you are solving. So is this quantum, that quantum, effectively sharing the equation, that sort of thing. So this phenomena is certain. We're talking about the same quantum mechanics phenomena in the same sort of not orange and apple, but really we're talking about the same thing.
Yeah, we are solving Schrödinger equation, that's for sure. Yeah, but this field or the system is so complicated. There is no translational symmetry, so really we cannot consider the system as a whole. We have to actually decompose it into individual chlorophyll, individual molecules, and then build a kind of effective model from that. From that basis.
Maybe I can say something.
Okay.
Okay. Because this system is a molecule base. Each electron in a molecule is binding. So yeah, he's not talking about electron transfer, charge not transfer, just energy transfer. So the electron is always stay in the same molecule, same site. So this is like a very tight binding system. Okay. So like a semiconductor, but no transfer electron. The basic same, but since you don't have a translational symmetry, the calculation will be very demanding. So each time you have to calculate those binding electrons. Okay? But basically same things. Okay?
So can quantum chemistry come into play?
Yeah.
Oh yeah.
Yeah. There's people use quantum chemistry to calculate all sorts of such as coupling between chlorophyls that can calculate it quite, I think, reasonably good nowadays in quantum chemistry. Energy of each site, each chlorophyll, excitation energy of each site that's probably not that accurate, but we can get good trend, for example. Okay, so I think that's a field that's very much been hardly pursued in chemistry. Right now, people try to use molecular dynamics simulations and quantum chemistries to gain more about those information in the system, to understand more about the system. But my point of view is, if you want to really look at the transport property and the total behavior, collective behavior in the system, then quantum chemistry is not enough. We need to go beyond that and really focus on dynamics. Okay. And in this sense, the effective Hamiltonian type of approach will be very, very important.